Hi everyone! In this video we are going to go over hydroboration oxidation of alkynes. So as usual, let's review how this works with alkenes and then we'll compare and contrast that to how this would work with alkynes. Alright, so recall that if we have an alkene, in order to perform hydroboration oxidation, we need to first add a molecule called borane tetrahydrofuran, and that's followed by hydrogen peroxide and sodium hydroxide. Okay, so you might have to look back at your notes, but what product would we get here? So is this a Markovnikov addition reaction, or is it an anti-Markovnikov addition reaction? And what functional group ends up forming at the end? So one really big clue here, we have hydrogen peroxide as one of our reagents. And whenever you see a peroxide, that pretty much means that you have anti-Markovnikov addition. And remember, anti-Markovnikov means that the functional group is going to add to the less substituted carbon. But which functional group are we adding here? Is it a halogen, an alcohol, a ketone? It's an alcohol. So we get an alcohol group that's going to add to the less substituted carbon on the double bond. Okay, so now let's apply this to alkynes. What happens when we perform hydroboration oxidation? Now the reaction that we're going to perform with our alkyne uses slightly different reagents. Instead of borane, we're going to use a different molecule that still has boron in it, but instead of being bonded to tetrahydrofuran, THF, it will be bonded to two alkyl groups. So remember, R just stands for some sort of alkyl group, so some carbon-hydrogen group. And then the second step stays the same, so we're still using hydrogen peroxide and sodium hydroxide. So this should still be an anti-Markovnikov addition since we're using hydrogen peroxide. Okay, so with an alkyne, we're going to still add an alcohol to the less substituted carbon, but that triple bond turns into a double bond. So if we have an alcohol next to an alkene, what do we call that molecule? We just learned about it in the last video. An enol. So if you have an alcohol next to a double bond, that's called an enol. And remember in the last video where we talked about acid catalyzed hydration, we said that enols in the presence of an acid will quickly transform into a ketone. And it does exist in equilibrium with the ketone, but the ketone is the preferred structure. Now, in this case, the alcohol is actually on the very end of the molecule instead of somewhere in the middle. So will we still end up with a ketone? No, because there's a hydrogen on the end. Just put that in there. So there's a little hydrogen. Okay, so instead of a ketone, what we're going to see is an aldehyde. because there's a hydrogen on the very end of that molecule. So there's still tautomerization occurring here, similar to acid-catalyzed hydration, but instead of a ketone, we end up with an aldehyde because the OH group is on the less substituted carbon. All right, so in general, the mechanism here involves the boron attaching to the less substituted carbon, and then it's later replaced with an alcohol group. So the boron attaches to the less substituted carbon and is later replaced with OH. But then, of course, as we just saw, that ends up forming an enol. And enols are going to very quickly turn into either ketones or aldehydes, depending on where it's located. Okay, so let's look at what that original reagent looks like, the R2BH. Let's look at some specific examples of that. So there are a couple of different ones we can use here. There's one molecule where boron is attached to the following, and this is called dicyamylborane. Now there's another one, and we'll see if I can draw it. It's not very easy to draw because it's a bicyclic compound. There we go. Okay, so this one is called 9-bora-bicyclo brackets 331 nonane. And that is a very long, complex name, so we typically abbreviate this as 9BBN. And I kind of like that one because it's just a cool name. So you'll probably notice that these are very bulky borane molecules, and the reason that we want to use a bulky molecule here is because it can only add to an alkyne, not an alkene. So we want a bulky borane molecule because it can only add to an alkyne, not an alkene. So for instance, if we used BH3 like in our alkene reaction, so if we use BH3, that's just going to keep reacting with the alkene. And then we just end up with a completely different product. And, you know, maybe that's what you want to happen, but for now we're just going to focus on forming aldehydes and ketones. Okay, so let's look at the mechanism of this a little more closely. Now, when we use a reagent like 9BBN, we end up with a base-catalyzed enol tautomerization. Whereas before, in the last video, we talked about acid-catalyzed tautomerization. So let's just show how this is different. So I'm just going to draw an alkyne here with our reagents, 9BBN, or you could also use the dicyamylborane. And we're again going to use hydrogen peroxide and sodium hydroxide in the second step. So in the first step, we're going to form our enol. So remember that involves adding the OH group to the least substituted carbon. And then the hydrogen will add to the more substituted carbon in this case. Okay, so there's our enol. And again, we know that it's going to turn into an aldehyde. However, the mechanism is a little bit different here compared to the acid-catalyzed hydration mechanism that we saw. In fact, it's basically the opposite of that mechanism. So we saw with acid-catalyzed hydration that the alkene grabs onto a hydrogen. And then from there we get to the ketone. But the first step here, I'm going to draw this a little differently. The first step for this tautomerization is the OH group from NaOH. That's going to come in and grab a hydrogen from the alcohol. And that's why this is called base-catalyzed tautomerization. All right, so now that's going to give us a negative oxygen, but the rest of the molecule stays the same. And now we're going to end up with some resonance structures here because that oxygen can now form a double bond with the carbon down below, and the pi electrons are going to be kicked over to the other carbon. So the negative charge is just moving along to the carbon. All right. Now in the last step of this tautomerization, the negative charge on the carbon is going to grab a hydrogen from water. And that's going to give us, let's see, H2, CH. Okay. So this is our aldehyde. Oh, and you know what? I'm going to flip around this CH3. I just kind of drew that backwards out of habit, but that might make more sense. So CH3, CH2, CH, and we have a double bond to oxygen. And then we also end up reforming the OH molecule as well. So that's why it's a base-catalyzed enol tautomerization. So again, this is a slightly different mechanism than the one we saw before with acid-catalyzed hydration, but it's basically just the opposite. Instead of adding a hydrogen, we are deprotonating first. One more note, the ion that we formed is called an enolate ion. So initially we had an enol and then we deprotonated it and that became the enolate ion. All right, so let's do a couple of practice problems. So in the first practice problem, I'm going to give you an alkyne. And you're going to perform hydroboration, oxidation on this alkyne. And then you're also going to perform this same reaction on a slightly different alkyne. And I want you to try to see what the products are here. All right, so if you want to pause the video and try this on your own first, feel free. And when you unpause, we'll go over it together. Okay, so for our first alkyne, let's see what our product would be. So we have anti-Markovnikov addition, and we know that we're going to end up with an aldehyde at the less substituted carbon. So the less substituted carbon I'll highlight in blue. So we know we get an aldehyde at that carbon. Now I'm just going to number my carbons on this substituent just so I can keep track of how many there are. Okay, so I've got a ring, and then I have 1 carbon, 2 carbons, and then 3 carbons, and then that's what my aldehyde is attached to. So 1, 2, 3. Okay, so now what about the other alkyne? What would our product look like? So again, we know that we're eventually going to get an aldehyde on the less substituted carbon, so I'll just highlight that one. And I'm going to number my carbons. 1, 2, 3, 4, 5, 6. Now, if I were trying to name the alkyne, I would have gone the other way because remember we want the alkyne to have the lowest number possible. But in this situation, I'm just trying to keep track of my carbons, so it doesn't really matter. All right, so I've got 1, 2, 3, 4, 5, 6. There's a methyl group on carbon 2, and there's an aldehyde on carbon 6. Okay, so 1, 2, 3, 4, 5, 6. Perfect. Okay, so if I, for instance, ask you to draw the product for a reaction like this one, and I don't tell you to draw the mechanism, now you know that you're just going from an alkyne to an aldehyde, and you just have to keep track of your carbons. Make sure you're not losing any carbons in the process, because it's very easy to do that. However, I do want you to know the acid-catalyzed enol tautomerization mechanism as well as the base-catalyzed version. That's just very important in organic chemistry, so definitely know this mechanism. And let's just summarize everything we talked about in the last 2 lectures because the acid-catalyzed hydration and then the hydroboration oxidation reactions, they end up forming similar molecules with either a ketone or an aldehyde. So let's just make a little chart kind of showing these reactions. So let's say initially we have a terminal alkyne. So the alkyne's at the end of the molecule. We saw that if you perform acid-catalyzed hydration, so you've got catalytic acid in water, and you're also using a catalyst mercuric sulfate, that's going to produce a ketone at the more substituted carbon. And then if you use hydroboration oxidation, so let's use 9 BBN followed by hydrogen peroxide and sodium hydroxide. That's going to give you an aldehyde at the less substituted carbon. Let's see. 1, 2. Oh gosh, I'm getting confused here. 1, 2, 3. There we go. Okay, now if we have an internal alkyne, and we haven't really talked about this yet with our hydroboration oxidation, but we can probably make some predictions here. So let's say we have an internal alkyne, so it's not on the very end, and it's asymmetrical. Let's perform hydroboration oxidation. Okay, now looking at our 2 carbons in the alkyne, so I'm just going to highlight them. Which one is more substituted and which one is less substituted? Or are they equally substituted? So both carbons are only bonded to one other, or I guess 2 other carbons technically, but they are equally substituted. Oops, didn't mean to do that. So these are equally substituted. So we could end up with 2 products. And remember, we saw this similarly with acid catalyzed hydration. So if you have an internal alkyne that's asymmetrical, you can end up with 2 products. So I'm actually going to highlight one of these as blue so we can differentiate them. And let's draw our 2 different products. Okay, so we've got 1, 2, 3, and let's highlight our carbons. So the first one is yellow, second one is blue, and then I'm going to draw this again, and then we'll add our functional group. Okay, so we could have equal probability of adding a carbonyl or like a ketone or aldehyde to either carbon, right? So let's say it adds to the yellow carbon. So let's say we add our double bond to oxygen on the yellow carbon. Okay, is that a ketone or an aldehyde? It's a ketone. Okay, so far we've only looked at examples where we produce an aldehyde because we were only using terminal alkynes. But if we use an internal alkyne and use hydroboration oxidation, we actually get ketones. So, just something to keep in mind. Now, again, there's equal probability that the functional group could add to the blue carbon. So let's add that. And we have our double bond to oxygen on the blue carbon. Now, is that a ketone or an aldehyde? It's a ketone again. Okay, so even though hydroboration oxidation goes through anti-Markovnikov addition, in this case, we have equally substituted carbons. So it could add, we're going to add our functional group to either carbon in this case. And because we have an internal alkyne, we actually end up with ketones. So kind of cool. All right, so now what would happen if instead of hydroboration oxidation, we performed the acid-catalyzed hydration reagents? What would our products look like? So typically, we would form ketones with this set of reagents, and the functional group would add to the more substituted carbon, right? So it goes through Markovnikov addition. But again, those carbons are equally substituted, so there's a 50-50 chance that the functional group ends up on the yellow carbon or the blue carbon. So we actually end up with exactly the same products. So if you had this reaction going, you could either perform hydroboration oxidation or acid-catalyzed hydration to get these products. I guess it would depend more so on, what's more environmentally friendly, what's less toxic, or what's readily available, depending on your situation. Okay, so I think we'll stop there today. In the next video, we will talk about halogenation of alkynes, and we'll also talk about ozonolysis of alkynes. So, of course, we'll review the same reactions with alkenes, and then we'll dive into how it works with alkynes. So I will see you then.